Hi everyone, it's Ian here from Crack Maths and welcome to tutorial 75 of the GCSE Foundation Maths series, which is all about irrational numbers and exact values. So I've put some questions up here for you to have a quick look at. If you are happy with these sorts of questions, then that is perfect. You can move on. If you are not happy with these questions, stick with me, and in this video we are going to look through exactly what are irrational numbers and what are exact values, and then we will be answering these 4 questions at the end. If you want any further practice on these types of questions, I also have a video available to you. I'll put the link in the description, which is just 20 questions and answers on this topic for you to just go through at your leisure if you feel like you don't quite need the description, but you just want to get going and have a go at the questions. Okay, so perfect. Right, let's get started with this tutorial. So here we go. Our first topic here is what are irrational numbers? Okay, so irrational numbers are numbers that have no sense of pattern. The most famous irrational number is the one that we use, which is pi. Okay, now you might recall from the past that pi we say is equal to 3.14. Well, when we say use pi as 3.14, what we're using a rounded version of pi, because actually pi goes on forever. So the numbers, if I remember correctly, it's 3.14159, and then I'm done. But there are actually competitions that exist in the world for knowing all of the values of pi. Let me show you here on the calculator. I've got a different calculator here for you today. So here we go. Here's the pi button. It will be somewhere different on your calculator. But there you go. When I put pi down there, you can see it says 3.1415926. In fact, let me write these down and I'm going to remove the calculator. 2, 6, 5, 3, 5, 9. Because what I'm going to do is I'm going to explain why you can tell from these digits that pi is irrational. So some decimals, you might have seen them before. You can get things that are recurring decimals. So say, for example, 1 over 3 equals 0.3333333, and so on. And these 3's go on forever. Now, even though these 3's go on forever, okay, these 3's here go on forever, we say that this is a rational number because we understand what's going to come next. There's no surprises here. It's 3.3333333333333. However, with pi, we've got 3.1415. So already we do not know what number is going to come after the 1. Okay, here we have 59. Okay, and here we have 53. Okay, so we still do not know what comes after a 5. In this section, that is largely all we can talk about. But the fact that those two things are there is what makes this number irrational. Okay, so an irrational number is a number where we cannot predict the next number in the decimal place. So usually, if something can be written as a fraction, okay, it is going to be, not even usually, always actually, if a number can be written as a fraction, it is going to be a rational number because we're always going to be able to predict what comes next. Let's take a look on the calculator at some different fractions that could work here. So let's say 2 over 7, okay? So let's see what happens on the calculator when I get 2 over 7. So that 2 over 7 means 2 divided by 7. So let's see. Here we go. Right, now what you can see here is we've got 0.285714. Okay, so that looks pretty, this section here looks pretty irrational. But actually what we see is what comes after this 4 is a 2, and then the pattern just repeats itself. So we've got 2 like here, 2. We've got 8 like here, 8. We've got 5 like here, 5. we've got 7 like here, 7, and we've got 1 like here, 1, 4 like here, 4. So 2 over 7 is rational because after every 2 comes an 8. After every 8 comes a 5. After every 5 comes a 7. After every 1 comes a 4. After every 4 comes a 2. Then after every 2 comes an 8. And so the pattern just continues, okay? You might have seen a situation a bit like this when we've done division using the bus stop method. So actually, let us take a quick look at this using the bus stop method. So here I've got 2 divided by 7, so that puts 2 here and 7 here. So 7 into 2 doesn't go, so we put our decimal place, we put a 0 here, and then we carry the 2 because we haven't used it yet. So remember, 20 here, this is the tenths column, is like 2 in the units column. Okay, so 7 into 20 goes twice, which is 14. And then so I take 14 away from the 20, which leaves us with 6. Then we have 7 into 60 goes 8 times. Okay, 8 times 7 is 56. So I'll put a 0 here and then a 4 there. 7 into 40 goes 5 times, which leaves 5 remainder. And then we've got 7 into 50 is 49. 7 times 7 is 49. So that goes in 7 times with 1 remainder. Then we've got 7s into 10 go once with a 3 remainder. Then 7s into 30 go 4 times with a remainder of 2. And as you can see, we're about to start. We've got this all over again, so it's going to kick off the same pattern. So 7s into 20 go twice with a remainder of 6. And then we just see this going on and on and on, continuing the pattern. So remember, if something's a fraction, it's going to be a rational number. Okay, so let's have a look at what else is an irrational number. So we know that pi is irrational. Okay, but what else? So, well, I'll tell you what else. Square roots which don't work. Okay, so obviously we can get something like, you might remember from a previous tutorial, we could have the square root of 36 equals 6, okay? Which means 36 is a square number and its square root is 6. But if we had the square root of 35, 35 isn't a square number. And when you square root something that isn't a square number, unless it's a multiple of a square number in certain capacities, like so for example, if it's like a decimalised version, because you can obviously you can multiply any number by itself. So if I multiplied something like 0.3 by 0.3, that would give me a value which would be 0.09, which would then have a square root, okay? But a lot of numbers that have square roots which aren't square numbers don't have nice solutions. So let's work out here. We've got the calculator. So I'm going to put the square root symbol there. And then let's try root 35. Here we go. Root 35. And we can see that this is 5.916079783. And we've already got enough information here to tell us that this number is irrational because we can see after this 7 becomes a 9, but after this 7 is an 8, okay? So there's no pattern to these numbers. So we'll say that root 35 is irrational. Let's try some more. A common irrational number that we come across is root 2. Okay, so here we go. The square root of 2 is irrational. And we can see this very quickly on because we've got 1.4142. So after the 4 here is a 1, and then after the 4 here is a 2. So there's no logic to this answer. There probably is somewhere, but not in our capacity. Okay, so that kind of covers irrational numbers. The thing that you should also know about irrational numbers is if an irrational number is multiplied by something, it's still irrational, okay? So something that we could have is 3 root 2, Okay, so this means 3 times root 2. Now, there isn't anything that you can multiply these numbers by which is going to magically cure them, except obviously themselves in the square root situation. So say, for example, I've got my square root 2 here. Let's say I times this by 3. Here we go. It's still the same sort of thing. No pattern to it. Still completely irrational. Okay. Another thing we could have something like pi divided by 5. Okay. So obviously we know that pi is irrational, but let's have a look at what happens when we divide it by 5. So here we go. We've got pi divided by 5. And there we go. It still makes no sense. So we've got here, after the 8 becomes a 3. After this 8 is a 5. We don't know what's after that 8. But after this one is an... Oh, that's a little bit of a pattern. After this one is an 8. After this one is an 8. Interesting. Have we got anything else we can compare? After this 3 is a 1. And after this 3 is a 0. Okay, so obviously when something is irrational, it could be that sometimes you see a similar glimpse of a pattern, but actually if you extrapolate that along the whole number, you will not see any pattern at all. Okay, right, so what this brings me on to next then is the idea of exact values. Now, because we do have these irrational numbers, if we convert our irrational number into an actual number, we will lose some accuracy. So for example, if I had to write down root 2 as a value, what I would do is I'd have root 2 here, so find the square root of 2. And this equals this, 1.4142. Okay, I'm going to leave that there to 4 decimal places. 4 decimal places is usually a lot further than we'd go in maths. But the problem with what I've done here, is that now, if I said root 2 equals this here, my number is no longer exact. It's pretty accurate, but it's not exact. So what we need to know is sometimes if a question asks us to leave our answer as an exact value, what it wants us to do is it wants us to leave it like this in the form of root 2, okay? Or pi or root 3 or any irrational number that could come along. Okay, so let's actually have a look at an example here. So let's say I've got a rectangle. And I'm going to say this length is root 3 and this length is 7. Okay, so the area of this rectangle will equal the length times the width, root 3 times 7. Now, if I was going to write this down as an answer, what I would do is I'd write this as 7 root 3. Okay, and let's say I had some units. I'd say 7 root 3 centimetres squared. Now this value here, you might think to yourself it's pretty meaningless because I've got no idea what number 7 root 3 is. However, this is the exact value of the area for this rectangle, and it allows whoever reads it to find out the exact area as well. Imagine if you were a computer program or something like that. This in a way would actually be more useful to you, okay? Because this is going to give you the exact value as opposed to the rounded value. So this here, so let's have a look though. If I wanted to find the rounded value for this, I would simply do, I'd get my calculator out and I would do 7 times the square root of 3. Here we go. And as you see, what I'd probably write down here would be 12.12 centimetres squared. Okay, so if I'm gonna pull this away, let me just talk about this here. So this here is the exact value, and this here is the rounded value. Okay, and that's that actually for that. These are the main things that we need to remember for this topic. So what I'm going to do now is I'm going to move on to those questions that we had at the start, and then we will continue from there. Right, so let's have a look at example 1. Example 1 says, which of these numbers is irrational? So we've got here pi over 3, 0.2121, root 16 over 3, and 9 over 3. Well, I know which one's irrational straight away because anything involving pi is irrational. So this is the solution to the irrational number, pi over 3. And you can check it using your calculator. Although I imagine this question might come up in the non-calculator paper. But let's just work it out here. So we've got pi over 3, which is pi divided by 3. Okay. And then let's see what that equals there. So there we go. We've got pi over 3 here. And as we can see that this is irrational, this 5 is followed by the 5. This 5 is followed by the 1. Now, 0.212121, we're expected to know that this is a decimal. Okay. Recurring decimal, so not irrational. This one here, root 16 over 3, okay? Well, root 16 is 4, so this is 4 over 3. And 4 over 3 will just give us a recurring decimal as well. So let's do that, 4 divided by 3. There we go. So although it goes on forever, we know that these 3's make sense. And then the next one that we had was 9 over 3, which we don't need to think about too much. 9 over 3 is just simply 3, which is an integer, so very rational. Number 3 is a number that we can really think about. Okay, so here we go. Which of these numbers is irrational? It was pi over 3. Right, let's have a look at example 2. So here we go. Example 2 is the area of a circle is given by pi times radius squared. Find the exact area of a circle with radius 6. Okay, so here we go. So area equals pi times 6 squared. Okay, 6 squared is 36. So this equals pi times 36. And whenever we have a symbol or an unknown or something like this in maths, what we do is we always write the number in front of it. So we'd write this as 36 pi. And this lack of space between them means that they're being multiplied together. Okay, so here we go. This is an area as well, actually, so I should give the units. So the area to this, the exact area, is 36 pi centimeters squared. Now, the reason why that's useful is because, as I said, that would be useful for a computer or a mass production thing that is going to want to be able to get everything really accurate. But if we wanted to make sense of that number, what we could just do is we do 36 times pi and get our rounded value. Okay, so here we go. So that value there, 36 pi, is roughly 113.097335529. But as this is a rounded value, it is not the exact area of the circle because these numbers go on forever, despite how significant or insignificant they might be. Okay, right, let's have a look at the example 3. And this says here, a square floor tile has sides 5 centimeters. The diagonal is root 50. Can the builder measure this diagonal exactly? Okay, well, there's only one way to find out. We need to work out what the square root of 50 is. Now, 50 isn't a square number, so I'm going to say no, and I'm going to hedge my bets that this is an irrational number. So let's find out. Clear this, square root 50, but let's just confirm it. And here we go. So root 50 equals 7.07106781117. And then something that always makes me feel like a real mathematician is putting these 3 dots here down, which means therefore, I'm going to write therefore irrational and cannot be measured exactly using a ruler. I guess maybe with some kind of like laser technology equipment, there could be a way of measuring this exactly. But largely, you're always going to have to round it, okay, because it's irrational. Right, let's have a look at example 4, and then we will conclude there. So here we go. Example 4 says, a square patio has an area of 20 meters squared. The area of a square is given by area equals side 2. Oh no, that is meant to say area equals side squared. Okay, so area equals side squared. Okay, find the exact value, find the exact length of one side. Okay, so if the area is 20, and that equals the side squared, we need to unsquare this. So the way that we unsquare something is to square root it. So if I put a bracket around this and I square root that, put a bracket around this and I square root that, what we get left with on this side is the square root of 20. What we get left with this side is the square root undoes the square. So that means that this just becomes side. So here we go, the side equals root 20, and root 20 we can find out again with the calculator, but I know it's going to be irrational because it's not a square number. So here we go, root 20 equals this. Okay, so when it says find the exact length of one side, we could say, I don't need to write this numbers down actually for this. What am I going to say? I forgot what I was going to say. Each side equals root 20 centimeters. Oh, no, not centimeters. Meters. Okay, wonderful. Right, well, thank you very much for watching that with me. If you want any more practice on this, there's loads of practice on crackmaths.co.uk. This was tutorial 75, and this is in the GCSE section, okay? So just make sure you have a look for that, and I'll put a link in the description as well, actually. So hope that is useful, and see you in another tutorial. Thank you very much. Goodbye.